design, while managing critical and parasitic drag, we'll need to optimize the shape, angle, and surface characteristics to minimize disruptions to airflow. Achieving laminar flow is especially challenging, as even slight surface imperfections or sharp edges can induce turbulence, which contributes to parasitic drag. Here's a refined approach to maintain laminar flow and reduce drag while introducing the structure into oncoming airflow effectively. 1. Understanding the drag components in this design. Parasitic drag. This is caused by surface imperfections and projections, like control surfaces that disrupt smooth airflow. Reducing it requires smooth surfaces and streamlined shapes. Induced drag occurs from lift generation, which is necessary here. However, with proper center of gravity alignment, lift distribution, and laminar flow over the wing, we can minimize it. Laminar flow goal. To reduce both induced and parasitic drag, we aim to maintain laminar flow as far back on the wing as possible. Laminar flow reduces friction drag and improves overall efficiency. 2. Optimizing wing shape and surface for laminar flow. Wing profile. Use a thin airfoil profile with a sharp leading edge, optimized for laminar flow, such as a modified NACA airfoil. This shape reduces the separation of air at higher speeds. Surface smoothing and coating. Ensure the wing and control surfaces are polished and use a hydrophobic or laminar flow enhancing coating. This minimizes micro disturbances that could prematurely trip laminar flow into turbulence. 3. Increasing the number of wing elements for enhanced control. Given that we're trying to maintain lateral laminar flow, breaking the wing into multiple sections can help. Multi-element wing structure. Introduce slats or flaps that are precisely aligned. This keeps the airflow attached across sections, which is essential in keeping laminar flow stable and minimizing drag. The main wing surface could feature 2 to 3 additional segments that slightly overlap to sustain consistent pressure distribution. Boundary layer management. Each wing element can incorporate a micro slit or small gap to vent out boundary layer air, especially near the trailing edge. This reduces the buildup of turbulent flow and helps maintain laminar flow over longer sections of the wing. Hammer 4. Adjusting center of gravity for efficient flow and pressure distribution. To ensure laminar introduction into oncoming airflow, CG placement relative to pressure center. Position the center of gravity close to the aerodynamic center but slightly forward, around 25% chord length. This subtle shift ensures that the initial flow attachment is smooth, which aids in laminar stability and keeps the flow locked to the surface without large pressure shifts that could induce turbulence.